Okay, continuing with the discussion on the symmetric slab. What we've done so far is we've arrived at our mode field plot, which includes the N effective, and it also includes the spacing between the mode curves, not only down at the critical angle, but also for any theta. And so getting this chart depends on getting this very first solution, which has to occur either numerically or it has to be done numerically or graphically using the tangent function. What I'm going to do now is I'm going to try to explain to you the appearance of these multiple modes and what they look like when they're actually in the waveguide. Okay. I'm going to go ahead and draw my waveguide sort of in a vertical configuration here, where I'm going to write in this cladding we have index N2, and in the core we have index N1. And I'm going to make a series of plots as a function of the y-axis, which is transverse to the waveguide, and plot out for you what the solutions to these different modes look like. The m equals 0 mode looks something like this. Basically what we get is we get sines and cosines for the profile inside the slab, but then we get exponential decay matched out in the cladding. Okay, here we get a simple sinusoid, and what I'm plotting here is the electric field magnitude. Okay, and so the electric field could be either positive or negative, and what we're going to get then is we're going to get another sinusoid inside the waveguide and more exponentials on the outside, and now we're going to get another sinusoid inside, exponential on the outside, and finally, if I can draw it, a higher order mode that looks like this. Hopefully this is very reminiscent of the modes on a guitar string, and there are many problems in physics which lead to the same type of things, and in order to find the values for the phase matching condition, essentially the phase matching condition is equivalent to solving for these electric fields within the waveguide, and actually doing the matching where we match this exponential decay up to a sinusoid. Okay, and when you do that, you get the same mode diagram that we got here. Okay, so either way leads to the same solutions. In any case, inside the waveguide, then the lowest order mode tends to look like a single bump of light traversing through. Okay, the second order mode, because the power is proportional to the square of the electric field, the second mode tends to look like two bumps, two little lumps of light, and the third mode, 1, 2, 3, etc. Okay, so this is a plot, sort of a plot of the power. Okay, and it turns out that you can actually see this in waveguides, especially in integrated optics waveguides. Okay, so one thing that's interesting about this is it helps explain something which seems kind of crazy. Let me go back to this plot, this mode diagram, and we're going to ask ourselves, suppose we do have multiple modes. Maybe I'll go back to this this mode diagram here, and suppose that this is my actual d over lambda value, and suppose that we see, okay, there are three modes here, and they're at three different zigzag angles. Which zigzag angle is the one closest to 90? It turns out it's the lowest order mode which has the zigzag angle closest to 90. The other ones have zigzag angles closer to theta c, and they're more directly sort of going down the waveguide. It's funny though that the one which has the highest effective index is also the one with the zigzag angle closest to 90 degrees. It seems counterintuitive. In other words, if you look at this waveguide and you find one mode that has this large critical angle, propagation zigzag angle, or the small zigzag angle, versus one that has this very large zigzag angle, which one would you think goes faster? It sure seems like this one would go faster, but this one has the higher and effective, and that means this one, I'm sorry, I just said it wrong. The mode with the largest zigzag angle has the highest refractive index. Right? Largest zigzag angle has the highest refractive index. So here is the largest zigzag angle, and this one has the largest and effective, and therefore this one has the slowest propagation speed. It seems counterintuitive. Why did this one seems like it would go a lot faster than this one? Why is that? Well, these mode field diagrams help explain that. And basically what's happening here is you can see that as we go to higher and higher order modes, we've got more and more of the energy, that is the field, out in the cladding. And the cladding has the lower index. Okay? And because the cladding has the lower index, it propagates faster. So we have more energy out in the lower index. We have more of our energy is propagating faster. Okay? And so that's why higher order modes propagate faster. Okay? Again, back to this diagram. We can see that higher order modes have a smaller zigzag angle. Higher order modes also have, therefore, the smaller effective index. And the smaller the effective index, the faster the mode. Okay, so these things have lower effective index. And so these have more of their energy out in the cladding, whereas this one has very little, the zeroth order mode has very little energy out in the cladding. Okay, so that's how these modes work. Just a very short little bit on mode confinement. Let me just give you the idea here, because I've got a lot of experience in mode confinement, as a matter of fact, in fabricating integrated optic waveguides. I'm going to go ahead and go from N1 down to N2, and I'm going to have my unitless waveguide thickness here, and I'm going to go ahead and show my first couple modes here, like this. Now I'm going to consider 3 different waveguide thicknesses. I'm going to consider this one first, then this one, then this one. Okay? In case number 1, what we're going to have is we're going to have a mode with a relatively low effective index. But we're going to only have one mode. Okay? In case number 2, we're going to have, again, only one mode, but we're going to have a higher effective index. And in case 3, we're going to have 2 modes. Okay? And so for integrated optics, we want one mode. And we want it to be confined to the waveguide. Okay? Good confinement means that we don't have little energy in the cladding. If we make integrated optics devices where a lot of the energy spills out into the cladding, then those modes tend to be very lossy. So good confinement leads to less loss, generally speaking. And it leads to less loss because most of the light is contained within the core, and imperfections in the boundary between the core and the cladding, which inevitably occur in fabrication, will have less of an effect and will have less of an effect on the loss. Those imperfections for poorly confined modes are really bad. So 3 is no good because we have 2 modes. 1 and 2 each have one mode. Which one has better mode confinement? Well, the amount of mode confinement is characterized by the effective index. If the effective index is closer to N2, then I have less confinement. I have more of my energy out in the cladding. And so situation number 1, having the smallest band effective, has a less confined mode than situation number 2. So situation number 2 has good mode confinement. So situation 1 has a poorly confined mode, and situation number 2 has a good confinement. Okay, sorry if that's too small. But I just wanted to throw that in there because I have a lot of experience in that in the practical world. Thanks.